Okay, so the final question for Chapter 2 and an introduction to statistical learning, so it's questions 7a through 7d. But before I start on that, I want to say that there are also applied questions at the end of every chapter, so there's conceptual and applied. And the applied questions for Chapter 2 really just try to get you familiar with either the R or Python coding language, depending on which book you have picked up. So we're going to skip those and just move right into the conceptual questions for Chapter 3 and then do the applied ones for every other chapter from there on out. We're just skipping the applied ones for Chapter 2. Okay, so in this question we're going to look at the kNearestNeighbor algorithm a little bit. And we're actually going to code, and we'll code in both R and in Python. Okay, so let's get into the question. So the table below presents some training data for a set of 6 observations. So there's 3 predictors. So we have 6 observations and 3 predictors: x1, x2, x3, and the outcome or the response variable is the color. Okay. So we can think of x1, x2, x3 as coordinates in a 3-dimensional plane, right? And so it's plotting these points. So point 1 just lies 3 units out on the x2 axis. Okay. Observation 4 lies 1 unit out on the x2 axis and 2 units out on the x3 axis. Okay. And then those points have a particular classification, red or green. All right. So now suppose that we have another observation where x1, x2, x3 are all 0. Okay. So the first thing we need to do is compute the Euclidean distance between each of these observations, predict which color it's going to be when we consider k equals 1 as well as k equals 3, and then think a little bit about what type of k value would be optimal. Okay, so again, you can read the questions for yourself here, and I'll address them one at a time. Okay, so first off, we need to compute the Euclidean distance for each of these observations for the test observation where x1, x2, x3 all equals 0. Okay, so the Euclidean distance is just the Pythagorean theorem, but we can generalize it to as many terms as we want, as many dimensions as we have in our data. Here, each one of these x1, x2, x3, each predictor variable is its own dimension. Okay, so we have 3 dimensions, and so here the distance would be given by x1 squared, or x1 minus 0, x2 minus squared, x2 minus 0 squared, x3 minus 0 squared. Okay, and so since all of these are just subtracting 0, we can just take 0 squared plus 3 squared plus 0 squared to find the Euclidean distance for point 1. And similarly for point 5, we can take negative 1 squared, 1, plus 0 squared, 0, plus 1 squared, 1, and sum those together and take the square root, and that would be 2. Okay, and so we can actually we're going to calculate that here in R, and then I'll run it in Python as well. Okay, but I'm going to create a data frame that should just copy this data or this data here, and then I'm going to calculate the distance. Okay, and so here's the formula for it, but this formula is just the R version of this here. Okay, so let me run that. Okay, so here is our data, as already seen, and then I've added a new column called dist from 0, all right, and that's just the equation that we already went through. And so now I have the distance from 0 for each one of these observations. Okay, let's run that in Python. So I am switching over to the Colab sheet for Python. Okay, and so I have I need to import the pandas and the NumPy packages. I'm going to create my data frame, and then I'm creating a new variable here for that data frame, and this is the formula to get the distance, just like we already had. And if I run that, you see that we have basically the same readout as we did in the R version. Okay, so switching back to the R. Okay. So what is the question? So what is our prediction with k equals 1 and with k equals 3, and why are those predictions what they are? Okay, so by k equals 1, that means that we are considering one nearest neighbor, and then k equals 3, we are considering the 3 nearest neighbors. Okay. So where are we here? BC. Actually, let's just look at the data and think our way through this. Okay. So if I have, where are we here? Okay, let's look at this one. So if I have the point 0, 0, 0, then that means that these distances from 0 are how far away each one of these observations are from 0. And so if I'm considering one nearest neighbor, I need to find the nearest neighbor, or the one with the least distance. And that here is 0.5 at a distance of about 1.4. And its classification is green. And so when k equals 1, then our new point, our test point, is also going to be green. Okay. So, but what about when we are considering k equals 3? Okay, for C, what happens when k equals 3? Okay. Well, now we're considering the 3 nearest neighbors, and we're taking a majority vote. So we already established that the nearest one is green, but the second nearest one here is red. And then if we go to the third nearest one, that looks like to be observation 2, and that is also red. And so by majority rules, the new data point, 0, 0, 0, should also be red. Okay? And so we can actually run some R code for that. So here I'm just going to add our new observation here as a new row in our data frame. And so I'll even display that data frame here. Okay, so we have the same data frame as above, but we have this new observation. Okay, we don't yet know its classification. And of course, it is 0 distance away from itself. All right. And then in R, with the package class, so I'm going to load the class package, I'm going to run the kNn command. Okay. So my kNn command, so I have my training data, which is just the first 6 observations for x1, x2, x3. Okay. My test observation is going to be the 7th row, okay, for x1, x2, x3. And then the classes are going to be the first 6 y labels: red, 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 green, green, red. Okay. And so now I'm going to predict the testing data with k equals 1 as well as k equals 3. Okay. And so now when I run that, I get, here's my readout. So for the first one, for k equals 1, I get green, which is what we said. And for the second one, we get red, which is what we said. Okay. So just switching quickly then over to Python to run that. Okay, so here I'm just adding on that additional row. Okay, so I define each of the variables, and then I'm going to append to df. Okay, I'm going to append row 7. Okay, and print it out. Okay, that's what we get. And then Python, running a lot of these machine learning algorithms is a little less simple in Python, but this is the code to do it. So we need to import the kNeightbors classifier from the sklearn package. Okay, I need to define my training data. Okay, which is x1 through x3, and it goes up to 5. But remember, there's 6 observations, and it's because Python starts counting at 0 rather than 1. And so if you're not familiar with that, that's what's going on there. Okay. I'm going to create my test data, which again is the 7th observation, but because we start counting at 6, or start counting at 0, the 7th observation is actually number 6. Okay. And now I'm going to apply the kNeightbors classifier for both k equals 1 and k equals 3. Okay? And I'm going to now fit the data to the training data. Okay? And then in order to predict y, this is a very convoluted process in Python. In order to predict y, I'm going to take the model that I just that I ran here, okay, and I'm going to predict. So I've trained it here, and now I'm going to predict the test observation. Okay, and so when I run that, I'm not sure what these warnings mean exactly. If you know, let me know. But we get the same predictions. With k equals 1, we get green. With k equals 3, we get red. Okay. Okay. So finally, in the Bayes decision boundary, or if the Bayes decision boundary is highly nonlinear, where are we at here? What type of value would we expect for k to be best, low or high? So considering few neighbors or considering many neighbors. Okay. Well, we'll get to this figure in a second, but just to think through it, if the Bayes decision boundary is highly nonlinear, it means that it's probably reasonably complex. Okay, and we already know from every other question in this chapter as well as the book that highly nonlinear or complicated relations and data require a flexible model, and a flexible model in kNearestNeighbors translates to considering fewer neighbors. And the reason is in kNearestNeighbors, every observation, it considers some number of nearest neighbors around it. Okay, and so if I'm considering a lot of neighbors, 100, well, that means that nearby points, this point and this point, are going to consider many of the same observations. Okay, and so they're going to have similar values, red or green, although this isn't red or green, but red or green, 1 or 2, black or white, whatever. And so the decision boundary is going to be smoother. But if I consider fewer nearest neighbors, then each data point is more likely to be considering data points that a nearby point is not considering. Okay, and so its decision can be different, right, than even a point that's reasonably nearby. Okay, and so then it can have a very nonlinear decision boundary, right? So if there really is a very nonlinear decision boundary, then a highly flexible model, which means considering fewer nearest neighbors, would probably be best. Okay, that's it. Thanks.